Ever pondered how languages are classified? Well, sit tight, as today we delve into the fascinating world of the Chomsky hierarchy. This classification system is named after Noam Chomsky, who introduced it in the 1950s. Its purpose? To organize formal languages into 4 categories, each with increasing generative power. Each level is characterized by the types of rules allowed in its grammar. So, whether you're a computer scientist, a linguist, or just an enthusiast, the Chomsky hierarchy offers a systematic way to understand languages and their complexities. It's not just a dry academic concept, it's an intricate system that helps us comprehend the relationships and limitations of different types of languages and grammars. And it's not just about rules and restrictions, but also about computational complexity and expressiveness. Now, let's start to unravel this intriguing classification, beginning with the most powerful type. Type 0 or unrestricted grammars stand at the top of the hierarchy, but what makes them so powerful? Unrestricted grammars are a fascinating breed. They are the most potent kind of grammar in the Chomsky hierarchy, and their strength lies in their freedom. Unlike other grammars, unrestricted grammars have rules with no specific conditions. They are unrestricted, hence the name. This lack of constraint means they can generate what we call recursively enumerable languages, a broad and diverse set of languages that includes all other types of languages within the hierarchy. But what does recursively enumerable mean? Well, it refers to the ability to list out all the possible strings in the language, given enough time. Think of it as a never-ending list of sentences, each one unique and following the rules of the grammar. It's a bit like having a machine that can spit out every possible sentence in a language, given enough time and resources. This unrestricted nature of Type 0 grammars makes them equivalent in power to Turing machines. Now, Turing machines are theoretical devices that capture the essential features of a general-purpose computer. They can perform any computation that can be done, given enough time. This equivalency means that unrestricted grammars can generate or recognize any language that a Turing machine can, which is pretty impressive if you ask me. However, with great power comes great complexity. The unrestricted nature of these grammars can lead to intricate and convoluted rules. This complexity can make them difficult to manage and understand, especially when compared to the more restricted grammars lower down the hierarchy. So there we have it, unrestricted grammars, the titans of the Chomsky hierarchy. They can generate an infinite variety of sentences, match the computational power of Turing machines, and encompass every other grammar type in their vast reach. Unrestricted grammars are certainly powerful, but their unrestricted nature can also make them complex. Now let's move on to a slightly less powerful, but still quite flexible type. Next in line, we have Type 1, also known as context-sensitive grammars. These grammars offer a unique blend of flexibility and restrictions. They have rules of the form alpha A beta goes to alpha gamma beta, where A is a non-terminal symbol, and alpha, beta, and gamma are strings of terminals and/or non-terminals, with gamma not being empty. In plain English, this means that a non-terminal symbol can be replaced by a string of symbols, but the replacement is context-sensitive. The context, represented by alpha and beta, must be present for the rule to apply. The languages generated by these grammars are referred to as context-sensitive languages. Now, this might sound a bit abstract, but bear with me. Think of a context-sensitive language as a language where the meaning of a word depends on the words around it. For example, in the English sentence, I read a book, the word read can mean different things depending on the tense of the sentence. The context changes the meaning. Now, where do context-sensitive grammars stand in the Chomsky hierarchy? They are less powerful than unrestricted grammars, which we've already discussed. This is because unrestricted grammars have no constraints on the form of their rules, whereas context-sensitive grammars do. However, context-sensitive grammars are more powerful than context-free grammars, which we'll explore next. While context-sensitive grammars consider the context or surrounding symbols in their rules, context-free grammars don't. This gives context-sensitive grammars more generative power. So, context-sensitive grammars sit comfortably in the middle of the Chomsky hierarchy. They offer a balance between the unrestricted power of Type 0 grammars and the strict structure of Type 2 and Type 3 grammars. Context-sensitive grammars give us a balance of power and structure. But what if we want even more structure? Enter context-free grammars. Type 2 or context-free grammars might sound less exciting, but they play a crucial role in many areas. Context-free grammars are fascinating. They have rules of a specific form. Each rule is like a transformation, where a non-terminal symbol, let's call it A, can transform into a string of terminals and maybe other non-terminals. We'll denote this string as beta, so each rule is written as A transforms into beta. Now you may ask, what's so special about this form of rule? Well, this form ensures that the transformation of A is independent of its context. In other words, it doesn't matter what symbols are before or after A, it can always transform into beta. The languages that context-free grammars generate are, unsurprisingly, known as context-free languages. These languages have a particular charm because they strike a balance between expressiveness and simplicity. They can describe more complex structures than regular languages, yet they're simpler than context-sensitive languages. But where do we see context-free grammars in action? They're everywhere in computer science. One of their most celebrated applications is in defining the syntax of programming languages. Yes, the programming languages you use daily, like Python, Java, or C++, their syntax is described using context-free grammars. So when you write a piece of code and it gets compiled or interpreted without any syntax errors, you can thank context-free grammars for that. They help the compiler or interpreter understand the structure of your code and ensure that it follows the rules of the programming language. To summarize, context-free grammars are like the middle children of the Chomsky hierarchy. They're not as powerful as unrestricted or context-sensitive grammars, but they're more powerful than regular grammars. They offer a balance of simplicity and power, and they play a vital role in areas like programming language design. Context-free grammars offer a balance of simplicity and power, but what if we want maximum simplicity? That's where regular grammars come in. Lastly, we have type 3 or regular grammars, the simplest type in the Chomsky hierarchy. Regular grammars, as their name suggests, follow a set of regular, straightforward rules. These rules are of the form A to AB or A to A, where A and B are non-terminal symbols, and A is a terminal symbol. In simpler terms, a non-terminal symbol can be replaced by a terminal symbol followed by another non-terminal symbol, or simply a terminal symbol. Now you might be wondering, what languages do these grammars generate? Well, the languages generated by regular grammars are known as regular languages. These are the simplest type of languages in the Chomsky hierarchy and are characterized by their regularity and simplicity. But don't let their simplicity fool you. Regular grammars may be the least powerful type in the Chomsky hierarchy, but they are still extremely important and widely used in computer science and computational linguistics. One of their main uses is in pattern matching. For example, when you use a search engine, it uses regular expressions, which are a type of regular grammar, to match your search terms with relevant results. Moreover, regular grammars play a crucial role in lexical analysis in compilers. A compiler is a program that translates code written in one programming language into another language that a computer can understand. The first step in this process is lexical analysis, where the compiler breaks down the code into individual words or tokens. Regular grammars are used to define the rules for this tokenization process, making them an essential part of the foundation of programming languages. So while regular grammars might be the simplest type in the Chomsky hierarchy, they are far from insignificant. They serve as a key component in various computational processes, from internet searches to programming. Regular grammars might be the simplest, but they are far from insignificant. Now, let's wrap things up. To sum up, the Chomsky hierarchy gives us a systematic way to classify formal languages based on their generative power. Starting from the top, we have unrestricted grammars, the most potent, capable of generating any recursively enumerable language, equating them to the power of Turing machines. Next, we have context-sensitive grammars, a step down in generative power, but still highly capable, generating context-sensitive languages. Then we move to context-free grammars, widely used in various programming languages due to their balance between power and simplicity, creating context-free languages. Finally, we have regular grammars, the least powerful but still vital, especially in areas like pattern matching and lexical analysis in compilers, generating regular languages. So next time you ponder about language classification, remember the Chomsky hierarchy. It's more than just a classification. It's a guide to understanding the power and limitations of different languages and grammars.